Thank you, Alain, and thanks to the organizers, thanks to the public for not having taken a long lunch break. I want to talk about some tension between finiteness and infinity or infiniteness in groups. So finiteness properties. Well, the strongest finiteness property, of course, of a group is being finite. But there are interesting relaxations of this. For example, being finitely generated, or slightly better, finitely presented. And I want to focus on a stronger one, written F infinity. So let me define it immediately. So G is F infinity if G is the fundamental group of a cell complex K. With finitely many cells in each dimension and acyclic. Bigger? Okay, I'll try. There's a danger I'll follow the path of Yves de Cornulier, of having a diameter tending to 0 during the talk. K cell complex, finitely many cells in each dimension, acyclic. Acyclic means, if you want, contractible universal cover. So equivalently, you can say that G acts on the universal cover of K on some space which is contractible, and such that the quotient has finitely many cells in each dimension, so finitely many orbits of cells in each dimension. So there's a universal construction it's larger, bigger. So a universal construction, which is, you can take co-limit of joins. You take this as a discrete set, and you take joins, so 2 copies, and then you put all the edges, then 3 copies, and you put all the edges, and so on. And then you take a co-limit of all of this. That's a huge space, and you quotient by G. G acts on this space. That's usually not the most efficient way of producing a cell complex on which you will act. Acyclic, yes, exactly, because the aspherical, yes. Thank you. So this is certainly not the most efficient way, but the connectivity of joints always increases. So in this way, you universally construct such a space. More efficiently, you will take one 0 cell, then you will put some edges from this cell to itself for all generators. And then the fundamental group of this object, which is just a bouquet of petals, one for each generator, will be a free group. And then, when you have such a thing, you will paste in a 2 cell for each relation, for each relator. In this manner, you obtain the correct fundamental group, except that this space is not spherical, probably. So then, well, you just make it spherical. So then you glue in higher dimensional spheres precisely to make it spherical. So for each genuine sphere in the skeleton that you had up to that moment. And in this manner, well, you just look at which spheres you have and you fill them in. And it could happen that a group has this nice property that you only have finitely many cells to glue in each dimension. So this is a nice class of groups, which is more restrictive than being finitely presented, which would just mean that the two skeleton of this space has finitely many cells. It contains finite groups. Essentially, this is the joint construction. So you have one edge for each group element. Then you put one triangle with G, H, and GH on the three sides for all choices of G and H in your finite group. These are the two cells. And then you put tetrahedra for each triple of group elements and so on. So finite groups have this property. It's closed under free products and also direct products, so more generally extensions. There's in fact a reformulation of this definition, which says that you act on the universal cover, so you act freely on some cell complex with finitely many orbits of cells in each dimension. But you could also ask that the action is not free, but just an action in which the stabilizers are themselves F infinity. It's an empty criterion if you act on a point, but in fact, it's very useful to prove that some groups are of type F infinity. This is Brown's criterion. So, OK, if action on K as above and stabilizes. So K tilde as above stabilizes of type F infinity. Good. So this is the finiteness property I am interested in for my talk. And on the other hand, there are lots of notions of infiniteness that we can come up with. But one, the classical notion of a set being infinite, which is that it contains a proper subset, isomorphic to itself. Or even more strongly, we might imagine a group G, which is isomorphic to two copies of itself. So definitely, if G is not the trivial group, this forces G to be infinite, just because of cardinality considerations. So I may ask, well, does there exist a group G, which is both finite in this sense and infinite in this sense? Well, I don't know.
In which sense?
Well, finite, not in the sense that it has finitely many elements, but it has a finite... Yes. Infinite in the sense that it's isomorphic to two copies of itself.
I see.
That's a way of saying that something is really large. It's so large that you can find infinitely many cosets, which are in some way, natural way, in bijection with the group. Well, this I don't know, yet there do exist examples of groups, and we saw some yesterday, which are of type F infinity. And these will be Thompsons groups. So close enough. Thompsons group T. And since I'll talk more about this group, let me give you the definition, or a way of seeing it. So this is very much related to Matoui's talk. I think he essentially gave a definition. I'll let you guess a definition of the group. We take X, a Cantor set, which I view as infinite sequences over an alphabet. And okay, yes. I will define a group of homeomorphisms of X. So T will be the set of H homeo, which have the property that when they act on an infinite sequence, in fact, they only require knowledge of some finite prefix of the sequence. So I may state this formally, I guess, as follows. There exists a function phi from x to n continuous, and h of uv is going to be of the form some u prime times v. So you keep the same suffix v in the action for every u, well, as soon as the length of u is at least 5 uv. I guess this is correct. It's probably difficult to understand. So there's a nice way of visualizing this. X is the boundary of a tree. And the tree has vertices, finite sequences over the alphabet 1 to k. Every infinite sequence is just a limit of points going deeper and deeper in the tree. Well, this u prime depends on h. So I didn't put the quantifiers as I should. There exists phi, and for every u, there exists u prime such that.
It's probably not use the same key though.
Sorry?
Not use the same key.
Oh, definitely not. So thanks to Yves' suggestion, we'll write it in this way. So I see my tree as follows. And I take a finite cut.
And what is the u prime? Sorry.
Yes. So for every u, which is a finite sequence, there exists u prime, a finite sequence of this one. Not necessarily of the same length. Exactly. So I look at a tree and I make one cut like this, or I should have done it probably here, and then I see 1, 2, 3 hanging trees away from this cut. I draw another tree, and I make another cut like this. And after having made these two cuts, I see one subtree here, one subtree here, one subtree here. And on this side, I see also 3 subtrees away from the cut. And I rearrange them in whichever way I want. So H here is determined by 2 finite cuts of T and a bijection between their leaves. I could have put the cuts a little bit higher and just extend it in a trivial manner. So I cannot really say that the group is the set of pairs of cuts and bijections. But definitely every element can be represented in this manner. So this function phi, which is continuous, just tells you how high you have to go. And after that, it's just a simple rearrangement. If you want translation, if you respect the standard embedding of the tree in the plane, say lexicographic. Good. So these are the elements of the group. And it so happens that it's not even obvious that this group is finitely generated. But it so happens that this group is of type F infinity. And in fact, there aren't that many examples of groups of type F infinity. So there are all of these where you can vary the arity k. And then there's a slight generalization of this due to Higman, where in fact, instead of acting on a tree, almost preserving the tree structure, you act on a finite collection of trees. So there would be two indices that parameterize these groups. And then there are a few other examples, and then there are the universal constructions that I described. I could also mention that there's another finiteness property that we also saw today and yesterday, which is residual finiteness. So the fact that for every non-trivial element of the group, you can find a finite quotient in which this element remains non-trivial. Well, this goes very strongly against this property, in fact. This group has a well-known property of being a non-Hopfian, meaning that the group contains a map which is surjective but not injective, just the projection to one of these factors. And a classical result of Maltsev says that such groups cannot be residually finite. So non-residually finite. HD, not residually. Okay, so I want to play more with these different notions. Finiteness, infinity.
So
In this
since
sense.
Thompson is not a solution to your equation, maybe you say what's close enough.
Well, it's not a solution, but if you picture these self-maps of the tree, you can act with one element of HT on this subtree and on that subtree. So it's a close enough solution in the sense that HT contains HT cross HT.
Just contains, no finite index or.
Oh, no, definitely not. Yeah. So in this way, this is a group which contains two copies of itself. That tends to make it large.
And possible with residually finite.
No.
But the Thompson group is just not residually finite because it's simple, which is a distinct reason.
Well, that's not really a reason. I mean, it's a stronger property.
But that's the one you specifically was what you proved.
I didn't prove anything. I cited things. Let me move now to self-similar groups, which will appear very much in the talk by Volodya Nekrashevich. Hello, Volodya. So this notion, which was also very much put forward by Slava Grigorchuk, is that of a group G, which will not be isomorphic to two copies of itself, but which comes equipped with a map homomorphism psi from G into a direct product of many copies of G itself, semi-direct sim k. And here I will have k copies. So I want you to view this as some additional structure on the group G. And it's also close to this notion in that every element of G can be represented by an element of this extension. I want you to think about these as decorated permutations. So if you mark points 1 up to k, and you draw a permutation by a standard diagram. As here, this is my way of representing an element of sim k. And on top of that, you write group elements on the edges of the permutation diagram. That's exactly an element of this extension, wreath product. And you multiply these decorated permutations just by putting them on top of each other. And you multiply the labels, as you should. So I think we agree also that that's a notion of infiniteness for a group. That's,
you require this as injective?
I will very soon. Let's require it now. I didn't want to do this now for a good reason, which is that how do we construct such homomorphisms? Well, I will give you two constructions. Well, you may define such a homomorphism on a group, which is exactly what you want, except that the map is not injective. And then you make it injective. So that's a fundamental example due to Grigorchuk, for which I will take for F a finitely presented group, 4 generators and relations A squared, B squared, C squared, D squared, BCD, which will be a free product of cyclic 2 on this element and a Klein group on these 3 elements. And I can define psi just by giving you its values. And instead of writing formulas, I will give you these decorated permutations. So A would go to this permutation. I take k equal to 2. For B, I will take this. For C, I will take this. And for D, I will take this. Oh, yes. When I don't write the labels, probably I mean a 1. Indeed. Yes. So this defines a homomorphism. You just check that the relators go to relators. But this map, psi hat, or whatever you want, at the level of F, has no reason to be injective. And it's not. Well, I quotient by its kernel, and I still get a well-defined map.
Wait, if I compute BCD, I see A cubed CDB.
No, you see A squared 1.
Oh, there's 1. Okay, sorry.
And then you see a cyclic permutation of BCD. Yes. So you're going to quotient the map, well, quotient F by the kernel of this map. Then you get an injective map from F mod kernel to F cross F extended. But you want it to go to the same group. So then you still have to quotient on the right. And then maybe there's again a kernel, and you keep quotienting, and so on. So G will be the maximal quotient of F on which this map psi is injective. Well, this is Grigorchuk's group. It's not Grigorchuk's definition. But it's equivalent.
So it's very clear it makes sense, and this quotient becomes compatible with all operations.
Well, yes. So you will define psi tilde, if you want, from F to F wreath sim 2 by these formulas. And then you will write N0 is the trivial subgroup, N plus 1 will be psi tilde inverse of N cross N. And then N infinity as the union of the NN. That's a well-defined group. And then G will be F mod N infinity. So by construction, this is really the least I have to quotient so as to obtain a well-defined injective map. Okay, so when we talk about self-similar groups, we really insist that this is an extra structure on the group, and we're always allowed to take for psi the trivial map. This is not very interesting. But we would rather be interested in cases in which this map is almost an isomorphism. So injective and a cofinite image, the finite index image. Then in that sense, we would say that this is a relaxation of this condition that a group is isomorphic to two copies of itself. So it so turns out that here, psi is almost bijective. Either in the sense that its image has finite index, or in the sense that there's a finite index subgroup of G and a corresponding finite index subgroup here. So a K contained in G and a K cross K contained in G cross G here, in such a way that you have actually the reverse inclusion. Good. So this group is as close as you can get to this property here, but it has the extra property that G is residually finite. So we got this extra finiteness property, which we did not have for the Higman-Thompson group. Now, the residual finiteness is probably something that you cannot see immediately from the definition. So I just wanted to say one word on it, which is that we can iterate the map psi. It will go from G to G cross G. And here you will have k to the n factors, and this semi-direct sim k to the n. And this k to, well, we don't get the full symmetric group. We only get, in fact, the iterated extensions of symmetric k. And in this manner, we see that G acts on a k-regular rooted tree. In fact, this symmetric k to the n would be the permutation of the vertices at distance k from the root. So if you want to define the tree action directly, you look at this map, and here you get a permutation. This permutation tells you how to exchange the k neighbors of the root. But you also have group elements here, and they themselves can give you a permutation by applying the map psi. So each of these can be split, if you want, into k edges, which themselves get permuted. And recursively, each of them can again be split into k edges. So in this way, we really see a k-regular tree appearing. Good. Another example. Which will, I understand, figure prominently in Volodya's talk, is if we take M, a topological space, say, M prime contained in M, and F from M prime to M covering. So degree K. Now, we may take a base point in M and look at F as the fundamental group of M at this base point. Then I need a little bit more data. So I will take a bijection. Between the numbers from 1 to k with the preimage, the fiber of the base point. And I will choose paths Li from the base point to I under this bijection in M. And now I can define the map psi as follows. If I'm given a loop gamma at the base point, I will associate to it a decorated permutation. So given some I have to define some j, and I have to put some label on it. Well, the construction is as follows. I lift, so I've got my base point here, and I've got a preimage I. I've got my loop gamma. Well, there exists a unique lift of this path by the covering. That's the property of being a covering. So this is the lift of gamma starting at I. Well, it has to end at another preimage of the base point. So you just define j to be this other preimage. And the label we'll put on the edge will be a loop delta, which is defined in the unique way of producing a loop at the base point starting from this data. Namely, I first follow Li, and then I follow Lj inverse. So that's a well-defined construction. In fact, the action on the rooted tree can be seen directly without doing this construction. The fundamental group acts by monodromy on the fibers of the covering. So the first level of the action is given here, but I can iterate the covering. F to the n will be from a smaller subset to m, a well-defined degree k to the n covering. And if I look at the iterated preimages of the base point, I see a tree of preimages. First, the preimages of star, and then the preimages of star branching away from it. And this tree is moved around by monodromy, by analytic continuation, if you want. And in this way, I define permutations of the tree of preimages. Okay, so all of these groups are, well, this group is residually finite. The group we obtained here comes with an action on the regular rooted tree. If this action is faithful, then you have shown that the group is residually finite. I don't want to impose the condition that the action is faithful. In fact, there are some interesting examples where it is not. But if it is, well, you're acting on a sequence of finite sets. First the root, then vertices at distance 1, then at distance 2, and so on. All of these are finite sets, and they approximate the action arbitrarily well. Good. So finiteness properties again. Well, recall that we had the map psi from G to G wreath symmetric K, which defines the structure of a self-similar group. We will say that it is contracting if there exists a finite subset N and the map phi from G to the naturals such that for all group elements, if I iterate phi of G times, oops, sorry, that was a psi. If I iterate phi of G times this map on the element G, then this will have all the decorations belonging to the set N. So here I guess we have k to the phi of G factors. So the under application of the map psi, the entries of the decorated permutations become simpler. Then it becomes simpler so much that if I do it sufficiently many times, then I get to some finite set. This is, so I should have mentioned this is Nekrashevich theory of iterated monodromy groups. If you want to get a residually finite group, then you can just look at the quotient of f that acts faithfully on the tree in this manner. And this is a very useful invariant, as he proved. So in case the map f is expanding, you see that these lifts here will become shorter. And in particular, we will have this contraction property. The Grigorchuk group is also a contracting group. In fact, the set N for the Grigorchuk group is precisely the generating set, ABCD, and the identity. Well, I guess I'm ready to state the theorem. Sorry?
What is Selfsimilar?
Well, this is G, and this is also G. That makes it self-similar. I think about self-similarity as being a recursive definition. So G is defined recursively in terms of itself. The elements of G are represented using elements of G themselves. So theorem by Ross Geoghegan and myself, which is that if G is self-similar and contracting, then G can be embedded in a group G hat, which is F infinity. And furthermore, this group G hat will have some additional nice properties. So G hat prime will be simple. And some extra desirable properties that you may want. So this G hat is constructed in a sort of abstract manner, but in fact, if G acts faithfully, on the tree or on the boundary of the tree by extending the action by continuity, then we might take G hat as the group generated by G and the Higman-Thompson group. HT, the group acting on X that we had before. And I still have 2 minutes.
In general, you have to indicate what abstraction for any group being embeddable. Maybe any group of that, yeah, from what you said, that's probably well known.
Yes, that's true. It's possible. So certainly uncountable group would not. There are that kind of restrictions. In theory, yes, it is possible that every countable group would embed in a group of type F infinity.
Well, if it embeds in a finitely presented group, it would at least need to be recursively presented.
Yes. So the criterion for embedding in a group with a two complex. Yes. So being of type F infinity gives you in some sense a reasonable control of the word problem. So the difficulty with the word problem is that you have relators and you don't really know how they combine with each other. If you have F infinity, then it means that the relations between the relators are in some sense controlled also. So I'm not aware of a group of type F infinity with an unsolvable word problem, for example. And I'm not sure that this can exist.
But it's a subgroup of such a group, is what you say.
Yes, but for a subgroup of a group with solvable word problem, it remains solvable. Yes. Yeah, I didn't mention this, but for example, if a group is automatic, then it's automatically F infinity, precisely because you can construct the cells one after the other, and you control very well the structure of the word problem. Yes, so I still have 30 seconds for the proof.
2 minutes according to that Swiss watch. That's the only Swiss item.
So for the proof, we construct an algebraic object of which G hat is the group of automorphisms. So we consider G-Cantor algebras.
G is for girl.
G would be the group. So a Cantor algebra, in the sense of universal algebra, is an algebra A with just one axiom, well, one operation, which would be mu, a k-array operation, and just one axiom, which says that mu is a bijection. So saying that it's a bijection is really universal algebra. It's just saying that there's an inverse. So the inverses would be written alpha 1 up to alpha k. That would go from A into A to the k. And then you compose these mu followed by the alphas or alpha followed by the mu's. That must be the identity. So this defines a universal algebra. So there are free objects and so on. That's for Cantor algebra. And we also give ourselves extra elements, lambda g, from A to A. So extra unary operations in the Cantor algebra. And they must satisfy some extra axioms. So certainly lambda g, lambda h is lambda gh. Multiplication in the group. And we use the self-similarity structure as follows, which is that if we have psi of g is a decorated permutation with a gi on this edge, then you would have the relation, I guess, alpha j lambda g equals lambda gi alpha I. So the permutation, sending I to j, and the entries g to gi are encoded in axioms.
What's alpha I?
That would be the inverse. So these are two axioms, and the other axioms are that mu composed with the alphas is the identity, and alphas composed with mu is the identity. Well, not the same identity. It's just the definition in terms of universal algebra. Okay, so as I said, I'm running over time, so let me just give you the statement. So you can look at CG, the free Cantor algebra, G-Cantor algebra. On a set of size 1. So the free object on a set of size 1, well, that's actually a very complicated Cantor algebra. And G hat will be the automorphism group of CG. It contains a copy of G precisely under these elements here. These lambda G, they would send the base point to an element in the Cantor algebra, which is base point times lambda G. And then you extend it uniquely because it's a free object. So it naturally contains a copy of G. And also under favorable circumstances, it is the same as this group here. Okay, so I don't have time to explain anything about the construction here. Just that if you have a free Cantor algebra, then you can look at bases. It's free on one object, but it's also free on more than one object. I mean, the free algebra on one generator can be isomorphic to the free algebra on 17 generators. So you look at the set of bases, namely the set of generating sets which give you a free object. And you can construct a cellular structure on this set of bases and show that this cellular structure has all the connectivity conditions that are required. So because the automorphism group G acts on the Cantor algebra, it also acts on the set of bases, and it acts on this cell complex. Okay, I guess this is enough for the proof. Thank you.
Yeah, okay, but you said you don't have example. There are some chances of construction of groups of some not problem acting in two-dimensional spaces, two-dimensional complexity. But we don't have very infinity in two-dimensional. They even have solve this problem, right? I can't can confirm it, right? Right, you have these two-dimensional complexes, which is spherical covering, contractible covering, and solve with this problem.
Well, probably that construction was given by Marx, I think.
Yeah.
Spherical.
Yeah.
Yeah.
So in two-dimensional, you have to
Yes, okay.
like much more than. So probably their construction is like we also do. It's very general construction, yeah. It's logical style construction.
So starting from a group, embed it using.
Yeah, but no, but it's very general construction, which allows you to construct very elaborate groups which are inside of a subgroup of two-dimensional spherical complex, finite. So it's, and it is certainly has much more implication.
Okay, thank you.
John.
How does this work relate to the work of Klaus Werber for the Grigorchuk group?
It relates very much in that his construction, in fact, is covered by this one. Maybe I can say it. So Klaus Werber constructed, indeed, an embedding of the Grigorchuk group in a group of type F infinity.
Is it actually the same embedding that we've got?
Yes, it is. It always gives this same one. And if you return to the definition of contracting, no, it's not here, of a contracting self-similar group, you may be so lucky that this set N would essentially be a subgroup, a finite subgroup. And in that case, there are some simplifications which are possible. So there is a work by Klaus Werber, and there were some extensions of, or generalizations of his work to cover this other case.
Peter.
If you take G to be the trivial group here, does that reduce to some well-known, to the original proof?
It does, yes, indeed. So this is a proof by Ross Geoghegan and Ken Brown, where indeed they considered these Cantor algebras and the bases as a tool for construction. The definition of Cantor algebra itself is due to Johnson, with a double S, a logician from the 60s. So it definitely predates all of this, and it arrives already in the very beginning of the study of these Higman-Thompson groups.
More questions? Okay, let's thank all the speakers of this morning session.